Hello. In this tutorial, we will analyze a propeller with the notions of design point and non-design performance. So here, for example, we have a propeller that has been designed for an upstream speed of 30 meters per second and a rotational speed of 4,500 rpm. We have thus defined the operating point in the operating point tab. We have therefore entered the speed of the fluid upstream and the speed of rotation. We clicked on Rebuild the blade with the optimum twist. So we now have a rebuild propeller with the optimum twist for these operating conditions. The propeller is updated to the new design point. We have its performance. We will see the information on the flow of the fluid through this propeller. We have several flow visualization possibilities, which are accessible with the Show menu from the 3D space. Then we have the possibility of showing the velocity vectors induced to the elements, or the possibility of showing the vortices free of losses at the tip of the blades. The vectors can also be rotated at the same time as the propeller. So here we have the various options. We are going to turn off the scatter plot display to see the vectors better. These vectors represent the stream of fluid whose upstream velocity is modified by the propeller in two ways. By the axial acceleration produced by the propeller. So we see the vectors which lengthen as they cross the propeller. We also see that their radius of distribution in the disk swept by the blades increases or decreases. With the increase in axial velocity, we observe a narrowing of the fluid stream, symbolized by the velocity vectors. The upstream fluid stream also undergoes a tangential impulse when the fluid stream crosses the helix. It undergoes a intangential rotation, which is symbolized by the tangential displacement of the vectors. So we have a tangential and axial deformation of the vector field representing the fluid stream. What we see in blue around it represents the vortices at the end of the blades. So this visualization is linked to the losses at the tip of the blades. The more loss we have at the tip of the blade, the greater these vortices will be. This schematic visualization of the induced velocities and of the stream of fluid crossing the propeller informs us about the quality of our propeller. We can also use the pressure distribution and the visualization of the boundary layers on the blades to understand various phenomena. We can highlight a stall phenomenon, or for a propeller in a fluid like water, the cavitation phenomenon, by visualizing the pressures. We are going to hide the particles. We are going to use the menu, model the distribution of pressures. Here, the pressure calculation has already been done. The calculation time to update the pressure distribution can take up to 10 minutes. Once it has been done, it is recorded, and whenever you ask for the visualization of the pressures, it will be done instantly. We stop the rotation. We see on the blade elements the distribution of pressures and depressions. So on the extrados, we see that we have a negative pressure scale, which goes from blue to red. And on the intrados, we have positive pressures. We also have the possibility to edit the boundary layer. We will select Show the boundary layer. The construction of the model is in progress. And so we see the boundary layer around the blade of our propeller. We will deactivate the display of the tree and isolate the blade to show us only one blade. So we still see our pressures, and we see the shape of our boundary layer around our blade, piece by piece. This can allow us to highlight stall phenomena. For example, we are going to use the out of design mode to view this propeller outside its operating point. The propeller is here drawn at its operating point. All performance is based on providing twist CL ratio divided by CD maximum. So there is no stall. We are really in optimum conditions. We see that our boundary layer is smooth and clean, with no turbulence phenomena. We are now going to modify the operating point. And for example, we are going to modify the speed of movement. And to think that we are at 0.1 meters per second. We could rebuild the propeller and redesign its twist to suit this operating point, but we won't. We'll calculate the performance at the current operating point, but without redoing the twist. We will observe the performance of this propeller twisted for another operating point by simply varying its speed of movement, so it could correspond to the case where we would have drawn a fixed pitch propeller for an airplane with an expected speed of 30 meters per second at 4,500 RPM. And we ask the question, what are its performances at 0.4 meters per second? And how the propeller behaves with a displacement speed close to zero. We are therefore rebuilding out of design, no update of the twist. We see that the performance has indeed been modified. We hide the axis. We will also hide the shaft and isolate the blade. We will show the boundary layer to see the stall phenomenon. This boundary layer calculation phase can take some time, because we are recalculating the boundary layer for each of the elements in this operating point out of design. Here is the calculation of our boundary layer and finished. It took about 2 minutes, and so we see our boundary layer, our flow around the profile. So we clearly see that the boundary layer is widened, and the profile has largely stalled. We see that the boundary layer is well away from the profile. So we clearly see the boundary layer largely unstuck around the series of profiles. We could also visualize the pressures. The pressures are calculated at the same time as the boundary layers. So in fact, when the boundary layer has been calculated, the pressure visualization is quite fast. Here, we can clearly see the boundary layer of our profiles. And we see that the profiles have largely stalled, and that the twisting is far from optimum for this operating point outside the design. To further highlight the phenomena around the profiles, we have the means of editing, element by element, the boundary layer and the pressure coefficients. If I select an element, I can start editing its pressure coefficients and its boundary layer. Then, I select the element, and I click. So we have two graphs appearing. Initially, we therefore see the boundary layer of the element. Therefore we see the layer on the extrados largely unhooked, and the layer on the intrados, which are not found at the trailing edge. It is a completely unhooked boundary layer. We could also have the pressure coefficient curve. We could thus analyze the flows element by element. So much for the visualization of boundary layers. on wing profiles or propeller blades. With Heliciel software,